Hello, everyone, and welcome back to Math Zone African Motives. We are still continuing with Grade 11 Physical Sciences. We are looking into Newton's laws. What we have done so far is to define the Newton's laws of motion, go deep into Newton's second law in terms of the relationship between force and acceleration. We have done the investigation. We have looked into questions that are in regard with the investigations and experiments that you'll be asked, that you'll be needed to know. So now, since we now know and understand the relationship that is there between the net force as well as the mass and acceleration, we now want to dive deep into the application, real life application of Newton's second law. How do we determine, how do we calculate the net resultant force where we have got more than one or two forces acting upon a body? How do we apply Newton's law on such objects? Maybe we have got two or more objects, we have got one object, but we have got more than one object, more than one force acting upon it. How do we determine different kinds of forces? This is where we are now, where we now want to dive deep into the resultant net force and how we apply Newton's second law in determining it. So, the first question to ask ourselves is, how do we determine net force using the second law? We know that net force can be determined through the vector sum of all forces acting on an object. When we mean vector sum, we are simply saying that whenever we have got one or more forces, we are saying that the net force becomes the sum of those individual forces, the vector sum of those individual forces, because net force is a vector. So we need to also consider both the direction and the magnitude of each force. So, by application of the Newton's second law, now this is where we get to say that the net resultant force, this is where we say the net resultant force is known to be equal to the mass times acceleration. So, the vector sum that we are saying we have to equate it to mass times acceleration, so that we get to say the vector sum of all forces should necessarily be equal to the mass times acceleration formula. This is where this law comes into play, so that it helps us to find or to determine the magnitude as well as the direction of the missing force, or else of the unknown force. So what we know is that when we are vector summing forces acting on an object, those that are acting in the same direction, we have to add them. Meaning to say that F1 plus F2 plus F3, it simply means that these would be directed in the same direction. And then those who would be acting in the opposite direction now, we now get to say that we need to subtract them. Meaning to say that if we are having, let's say, F2 in this direction and F3 in this direction, whilst F1 is in that direction, then we then get to choose a positive direction. If we say to the right is positive, then that's when we say that the vector sum of these forces, which will give us the net resultant force, should now be equal to F3 plus F2, which are in the positive direction, minus the one that is in the negative direction. That is what we simply mean by those in the opposite direction, we need to subtract them. So after we have done that, now that we understand that or what vector sum means, we now simply need to actually get to look into the formulation. The net force is equal to the net mass as well as the what? Net acceleration. Where we are now saying that from this relationship, we would get to know that whenever the net force is equal to 0, it means that there is no acceleration. Or else whenever acceleration of a body is equal to 0, then it simply means that net force is equal to 0. How do we get our acceleration to be equal to 0? This is where our speed or else our velocity is what? Is constant. Whenever we know that the object upon which our net force is acting is moving at a constant velocity, then it simply means that our net force is equal to 0 because the acceleration there would be 0. We need to pay particular attention to this concept because it will be used in a lot of scenarios. They will tell you that the object is being pulled at a constant velocity, and then there is a certain force acting in this direction, and then there is friction, there is that force which is inclined. Calculate maybe the frictional force or this or that. Just know that whenever there is constant velocity, then it simply means that the acceleration is 0 and the net force is 0. So it simply means that the vector sum of all forces that are acting on that object, they need to be equated to 0. But however, whenever that you are told that the speed or else the velocity of the object is changing with time, either it is decreasing or else it is increasing, you now need to know that the net force of that object is not equal to 0. Certainly the net force is equal to a value which is greater than 0 or else which might be not equal to what? To 0. So that is what we really need to understand and to know in terms of the definition of the net resultant force as well as the definition of the what? Of the Newton's law. Now that we now understand and we now know how to define Newton's second law and the resultant net force, now let's now dive deep into how we apply these two concepts in determining the net resultant force as well as determining individual forces acting on a body. Given that we might know the net resultant acceleration, or else maybe the acceleration is 0, or else at some point in time we need to calculate the acceleration itself. So I've brought to you exam question papers that I took from past question papers for practice sake, so that we might see how questions are asked and what is it that will be required to do and how would be required to determine certain aspects and how would be required to apply Newton's second law as well as the definition of the net resultant force. So here I've got question number 3. So I only took part where we would be applying the Newton's second law in answering questions to do with more than one force acting on the body, as well as at some point in time having 2 or more bodies, so that we can be able to determine the net resultant force as well as the missing elements, which might either be the acceleration of the object or else different types of forces. So before I start diving into this, I would simply like to identify different types of forces. So we would know that we have got different types of forces where we have got contact forces and non-contact forces. Where contact forces, these are forces that you would find in between two interacting bodies where there is contact, like where there is push, where there is a pull, there is contact there. And then where we mean that there are non-contact forces, this is where we have got forces interacting due maybe to the field that they are in. For example, gravitational force, it is due to the gravitational interaction. There is no contact there. And then we have got electrostatic forces, electromagnetic forces. Those forces, they are there, but there is no contact. And then within those forces, we now need to know different types of forces, like we have got tension. This is the type of forces where or else which exist in between strings, in between ropes, in between struts. And then we have got what we call the normal force. These forces, I've gone to define them deeply into the videos that I've done where we did combined classes for both grade 11 and grade 12, where we are defining forces as well as Newton's laws. Why we did that is that it's because you would see that this topic it comes handy both in grade 11 and in grade 12. You would be both examinable on this topic in both grade 11 and grade 12. So the definitions that we used for tension, normal forces, gravitational forces, which we said it's our weight, as well as the net resultant force, as well as your frictional forces, will always be the same. All you need to know is how to identify them and how to define them, how to determine them. We have done that in greater depth when we're doing those videos. If you did not manage to watch those videos, I would strongly advise you to go and watch those videos so that you might have full depth in terms of notes on how to identify as well as to determine different types of forces, so that here when we are now answering questions, we can be able to follow through as we identify different types of forces that are actually acting upon our bodies. So without wasting time, allow me to dive deep into the question. So we are going to do question number 3.2, which says that the sketch that you can see below here shows a block Q. This is the block Q of mass 1.5 kg placed on a rough horizontal surface. Block Q is attached to another block of mass M by an inextensive string that passes over a frictionless pulley. The blocks are stationary and the static frictional force between the surface and the block is 50 newtons. So we are told that these two blocks, they are stationary, and the static frictional force in between these two blocks, the static frictional force, which we said might be represented by Fs, is equal to 50 newtons. And then now they're saying the tension in the cord is T. Now, let's go ahead and see what follows in terms of the questions. What is it that we are required to determine? Now, they're saying, what is the magnitude of this tension? So, one thing that I would advise when you are now answering these questions, you need to determine and look into the forces that are acting on each individual block. For example, I would go on and say, let's look into the forces that are acting on block Q and the forces that are acting on block P separately. So forces that are acting on block M, on block P, you would come and say forces acting on block P. So you would come and determine those forces. So we can see that due to the mass M, we have got the weight of this block, which would be given by mg. So here, where g, it's 9.8. So you would know that you have got your weight. The weight is going downwards. And then you have got going upwards due to this string. You would have your what? Your tension. So here I would be having my tension. And then for us here, we need to determine the net force. So here we've been told that since the object, they are actually stationary, it simply means that there is no acceleration. Once there is no acceleration, what it simply means is that our net force, we have said that whenever there is no acceleration, our net force will be equal to 0, because we are saying that acceleration is 0. Therefore, now the vector sum of our individual forces is given by what? The vector sum of our individual forces is given by our weight as well as our tension. So these are our forces 1 and 2. Now we now need to determine a positive, let's say, a positive direction. Now we'll take going downwards as positive. Going downwards as positive. So our weight would be positive plus our negative what? Tension. So you would say W minus T is equals to 0. If that is the case, you would see that tension is directly or else is just simply equal to the weight of this object. But however, you would see that we only know the gravitational acceleration, which is 9.8, and then the mass being given as m. So we now have got two unknowns, which is the tension and the mass of this object. Now, let's go ahead and look unto the what? Let's go ahead and look unto the forces that are acting on the what? That are acting on the block Q. So you would come and say forces acting on block Q. You also get to determine and look into the forces. So we also know that there is F net, which is supposed to be equal to MA, which is also supposed to be equal to the vector sum of all individual forces. So on block Q, we know that since we said going down is the positive direction, so we are saying this block is being pulled towards the left. So definitely would be having our frictional force going that side. And then we would have our tension also going that side, which is due to the string, as well as if there was any force that is applied. But here we only have got the tension as well as the frictional force. So you would see that the vector sum would say tension is the one that is positive. T minus our what? Let me get to say that here, our frictional force is due to the static frictional force. Why? Because they said the object is stationary. And then here, because the acceleration is zero, definitely our net force is zero. So we have T minus Fs. So our static frictional force is equal to our tension. And we have been given the value of this to be equal to 50 newtons. So our tension is equal to 50 newtons. So by simply looking into the forces acting on these individual blocks, we have determined our tension, given that these blocks are stationary. So our tension here would be equal to what? To 50 newtons. We can simply go ahead as well and determine our mass, because already this other side, we have already said that our tension here, from what we have said, our tension is equal to 9.8 m. So here, since our tension is 50 newtons, we can now say 9.8 m is equal to 50 newtons. So my mass can be simply equal to what? 15 divided by 9.8. So you can determine that mass by saying 15 divided by 9.8. And that can give you what? What can be our result there? What can be our result in mass? So you would see that if you say 15 divided by what? 9.8, that would give you what? If you say 15 divided by 9.8, that would give you 1.53. That would be 1.53 kgs. So that would have been the mass of our object, given that that is the situation that we have. But however, here we're only asked to find the magnitude of the tension. Now let's go ahead and see the following question. So the following question now gets to say that. The following question is now saying, the mass of the block P is now doubled. Mean to say we now have got 2m for block P. The mass of block P is now 2m in kgs. If that is the case, resulting in the 1.5 kg, which is block Q, accelerating to the left. Now the acceleration is towards the left, and then they're saying the kinetic frictional force experienced by block Q is 14.75 newtons. By applying Newton's second law of motion separately to each of the blocks, calculate the magnitude of the acceleration of block P. So there is some information that we carry forward from question 3.21, which is that to do with our mass M, which we said our mass M is now being given by 15 divided by what? 9.8, which is equals to 1.53 kgs. This mass M, we have to carry it forward. But however, what we are now having as new information, is that, let's go back to that diagram so that we can be able to see what's happening. So I would like you to allow me to just get to rub through everything here. I just want to rub through everything here so that we can actually have our body free and we can be able to see what is it that they want us to find out. So we simply apply the same tactics that we have applied before, which is to say that you have to individually or separately look into the forces that are acting on the individual block, and then thereafter, using the net resultant law, which is the Newton's second law, we then look into what comes next. So now they are saying the mass of block P is now doubled, to say that now this is now equal to 2m. If that is the case, they are now telling us that the frictional or else the kinetic frictional force, we are no longer having the static frictional force, we are now having the kinetic frictional force being equal to 14.75 newtons, and the body is now accelerating that side. So definitely we now have our net force being equal to ma. We now have got some acceleration there. So how do we get to determine the missing values or else the missing variables there, given that information? This is where now we get to come and say, they said we now have got this 1.5 kg accelerating towards the left. After accelerating towards the left, we now have got our block Q being subjected to 14.75 Newton frictional force. And they want us to apply Newton's second law of motion separately to each block to calculate the magnitude of the acceleration of the blocks. So if that is the case, I'll simply go on to do this. Let's look at block P for a moment. So we'll start by looking into forces acting on block P. Forces acting on block P. Since they say they want us to look into the or else to apply Newton's second law on the two individual blocks separately. So I would say F net, according to Newton's second law, F net is equal to ma. After that, I know that ma is equals to summation of what? Of all vector forces that are acting on that block. Now, the vector forces acting on block P, we said we have got tension, and then we also have got our weight. And going down is our positive. Therefore, we would have weight minus tension being equal to ma. And what is the mass of ma? We have 2ma, which is equal to mg minus our tension. Now, this m, we have already determined this m, because there was a time where we said 15 was equal to m times what? Times 9.8. Now, that gave us our m being equal to 15 over 9.8. Given that, we would simply take that value, which we said it will give us 1.53, or else I would come and say 2 times 15 divided by 9.8 times our acceleration is equal to, we have m being the same, 15 over 9.8 times what? 9.8 there minus t. So you will see that these ones, they will cancel out. So I'll be left with 15 minus the tension, which is equal to, now I now need to actually guess to what? To determine that. So by having that, I'll multiply by 2. I would have 3.06 times my acceleration. So that is my first equation that I will have according to what? To block P. That is my first equation that I have. Given that, I will now go on and look into block Q. I'll look on onto the forces on what? On block Q. So I will come here and say, what are the forces that are acting on block Q? What are the forces that are acting on block Q? I would come and say forces acting on block Q. So for forces acting on block Q, I have got my Newton's second law, F net being equal to ma, which is also equal to the vector sum of all forces acting on our body. So on block Q, the forces that are acting on our body, we've got our tension, which is going to that side, our frictional force going to that side, and we have got that side being positive. So this one would come to say, I've got my tension minus my what? My kinetic frictional force. Given that, I would come and say my mass here it's 1.5, so I would have 1.5. I would have 1.5 times my acceleration being equal to my tension is not known. I would say T minus my frictional force 14.75 newtons. Now, what I can do is I now have got what? I now have got my second equation. My first equation was saying 3.06 times A is equal to my what? My tension, or else it was equal to what? It was equal to 15 minus my tension. It was 15 minus tension. That was my equation 1. That being the case, I will now need to use equation 1 and equation 2 to form equation 3. So what I can do is I can simply equate everything to T here on equation what? I would transpose, or else I would transpose this value that side, so that equation 2 becomes T being equal to 1.5A plus 14.75. That becomes my equation 2. That is my new equation 2. I will now substitute equation 2 into equation 1. So I now have got my new equation 2. I'll substitute my new equation 2 into equation 1. By doing that, I have 3.06A as my equation 1 equal to 15 minus where I've got tension. I'll now substitute that. That is 1.5A, and then also I would also have minus 14.75. Given that, let me just get to pull this one this side so that we can see. Given that, I will try to collect like terms by taking this that other side. It will become 3.06 plus 1.5 bracket A equal to 15 minus 14.75. So my acceleration will simply be equal to 15 minus 14.75, all divided by what? All divided by 4.56. And that gives me an acceleration of what? That gives me an acceleration of, if I say 15 minus 14.75, we are saying 15 minus 14.75, 0.25 divided by 4.56. That will give me an acceleration of 0.055 meters per square second. 0.055 meters per square second. Now, is that what we were asked to find? We were asked to find both. They said by applying Newton's second law of motion separately to each of the blocks, calculate the magnitude of the acceleration of the block P. So the magnitude of the acceleration of this block would simply be equal to what? It will simply be equal to 0.055 meters per square second. That is the magnitude of the acceleration. That is how we apply the Newton's second law as well as the net resultant force definition. After we have said that, let's look on the next, or on the coming equation. So this is our next question. We are still on the net resultant force as well as Newton's second law. We want to use the definition of the net resultant force as well as the Newton's second law to determine the missing values of any variable. It might either be the acceleration, it might either be one of the forces. We want to use those two definitions and laws to determine any of the missing variables. So now, Question number 3.3 was saying a constant force F that we can see here is applied to a 6 kg block to move it up a rough surface inclined at 60 degrees to the horizontal. Force F, which is parallel to the incline, moves the block up the incline at constant velocity. So here we have got constant velocity. What is it that we know about constant velocity? Acceleration is there. The block experiences a constant kinetic frictional force of 12.25 newtons. Draw a free body diagram showing all the forces acting on block P. As I have said, and I will always and I will continuously advise, we have done videos that combined lessons and lectures for grade 11 and grade 12 where we defined forces, and after defined forces we determined how you can calculate each and every force, and we also determined how we draw force diagrams and free body diagrams. Now we are now just applying those in regards to what the syllabus of grade 11 would need you to do. So let's go and check on that combined grade 11 and grade 12 classes for forces and Newton's laws, so that we can come back and dwell much on our grade 11 once we have those basics. So after I've said that, now let's look into that block. You can see that due to this mass, you would have its weight, which is always directed downwards. And then due to this force, the applied force, we would have the force going that way. That would be our F. And then due to the frictional force, it will always try to oppose motion. So we would have our frictional force here. After that, we will have a normal force that will be due to this inclined surface that would be going up. So when you are drawing a free body diagram, you use a dot to represent this block, and then you use a vector arrows to represent different forces that are there. And these are the forces that we have determined that would be acting on our what? On our body. Where now I'll be drawing the frictional force, and then going down I'll be drawing my what? My weight. And then I would now have my normal force. I would have my what? My normal force. So at some point in time, maybe I was just supposed to draw a neat diagram like this, where I'll draw this dot, my applied force, my frictional force, my weight, and my normal force. That is the free body diagram. And the number of marks gives you a hint or an indication on how many forces you need to draw there. And those are the forces that we have determined. And then there are some other people who would go a step ahead or else a step forward and resolve. They are going to resolve this weight into its two different weight components, where you would have your perpendicular weight component and your parallel weight component. So in some other instance, you would come and draw a free body diagram that is having a parallel weight component, and then that is also having a what? A perpendicular weight component. That would be now the one balancing the what? The normal force. That would be the one that would be balancing your normal force. And then you would have your force, that is the applied force, as well as your frictional force here. So it's still the same thing. You have just resolved this one force into two different forces. So you would be having your perpendicular weight force, you would be having your parallel weight force, and then you would be having a normal force. You can see that we still have got our weight that was resolved into two different forces, and then our frictional force, our normal force, and our applied force is still one and the same thing. After we've said that, now they are saying calculate the magnitude of F. They now want us to calculate the magnitude of F. How do we calculate the magnitude of F now? We have been told that our net force here is equal to 0. Why? Because we have got constant velocity. Constant velocity tells us zero acceleration. Zero acceleration tells us net force equal to 0. If that is the case, and we are saying that the object is moving at a constant velocity, it simply means that it is moving upwards and it is facing a frictional force that is going downwards. So now you would see that this F is equal to the frictional force as well as this perpendicular weight component. That becomes the importance of resolving your weight component into its two different what components, where you would have your weight parallel component and your perpendicular what and your perpendicular weight component, where you would know that this force now, since we are saying that F net is equal to 0, it means the vector sum of forces is also equal to 0. So I would come and say I have got going what going up to be positive. I would take F, this is 0, F minus this weight parallel component minus that frictional force. So I would simply say that this F is equal to W plus FR. If that is the case, I'll now come and say, what is this? This is mg sine theta. Mg sine theta. We have done the component resolution of our weight component in an inclined, and we have agreed that whenever we have got something like this, we will always have a weight component parallel, a parallel weight component like that and a perpendicular weight component like that, where this parallel weight component will always be given by mg sine theta, and this one will always be given by what? Mg cos theta. If you did not watch that video where we delved deep into this, please go and watch the combined grade 11 and grade 12 video on forces and Newton's laws. We have done this. So by knowing this, we just come and apply it here. So since I have demonstrated what we need to do here, let me take time to actually get to find where we have got enough space to actually get to determine our magnitude of our applied force. Now, I will take this space to come and say, if I were you, I would come and say 3.32. And then I will say F net is equal to MA. Given that I know that my acceleration is equal to 0, therefore my F net is equal to 0. So I would say I know that summation of what? Vector sum of forces is equal to my what? To my F net, which is equal to 0. Knowing that vector sum of my all forces, I said that I have got my applied force here being equivalent to my frictional kinetic force as well as my parallel weight component. So I would come here and say going up is positive. So I would take F being positive minus W parallel minus Fk, which is equal to 0. I would transpose these negatives to that side so that they become positive. So I would have F being equal to W parallel plus Fk, which is simply equal to what? I can simply come and say my F is now therefore equal to, so I'll say therefore F is equal to mg sine theta plus my frictional what? Kinetic force. And I know that this would simply be, my mass is 6 kgs, and then 9.8, which is my gravitational acceleration. I know that G is always equal to 9.8 meters per square second. We will always be given this, and then sine, my angle there is 60, and then I'll say plus What is the frictional force that was given there? They say the kinetic frictional force is 12.25. That is the one that I use here. And then I would come and say plus 12.25 newtons. And then my F will now be equal to. Now I just need to determine, I will just come and say 6 times 9.8 sine 60 is equals to 50.922 plus 12.25. That will give me what? That will give me 63. That is F is equals to 63, comma 17 0.2 newtons. It will be 17.2 what? Newtons. So that is the magnitude of the what? Of the force applied, according to our calculations using those two laws. Now they are saying the angle of the incline is now increased to 75 degrees. This is the angle that they are talking about. Let's say we increase this angle to 75 degrees. That is what we now want to know. What happens here? I'm sure that is what they want to know. Now, the angle of the incline is now increased to 75 degrees. How will this affect the magnitude of the velocity of the block as it moves up the incline if the force F acting on it remains constant? So if the force F remains constant, and now we have got a greater incline. At first, the object was actually inclined to this. We were having 60. We are now having what? 75. From just logic, from what you can see here, and we are still having the same F. From what you can see here, you would see that the block will now want to actually slide down because the incline is now great. So therefore, the velocity here has to decrease. The velocity will what? Will decrease. They said choose increase, decrease, or remain the same. The velocity will decrease. The velocity of the object going up is the one that is going to decrease. Why? Because the object will now want to start sliding down. Once we now have our object like this, the object will now want to start sliding down. Hence, therefore, the weight parallel component is going to increase. We are saying that W prime prime is going the W prime prime that we are going to get now will be greater than the initial W prime prime. Therefore, if that is the case, since our F is remaining constant, we are saying that since our F is remaining constant and W prime prime is actually increasing, we can simply see that. So we can say that this frictional force, if it is going to remain constant, this will change and this remains constant. Therefore, it simply means that the net force would actually be what? Will actually be less. So therefore, this one would actually what? Will actually affect the velocity going up. So the velocity going up will decrease. The velocity going up will what? Will decrease. They said choose from increase, decrease, or remain the same. You can either just use logic. Logic tells you that once we have got our incline increasing like this, this block will now start to sliding downwards. And then when it comes to calculations, we know that our velocity will now depend on the net acceleration of the object. So now we have got net acceleration. Net acceleration is dependent on the net force applied. So we would be having something like this. Now, net force is dependent on the vector sum of forces. Now, the vector sum of forces, from what we have seen there on top, we said the vector sum of forces, we are having something like this. Going up being positive F minus W prime prime minus our kinetic frictional force. Let's keep these two constant. Now this has increased. So let's say, for example, this was 10 minus our what? Let's say maybe this was 100. Let me take to say, okay, fine. The force applied, the force that we got there it's 63.17. So this one now, initially, W prime prime was 6 times 9.8 times sine 60, which would be 50, comma. Now, W prime prime, it's now 6 times 9.8 times 9, sine 75. This will give you a greater value. That is to say, that now we now have got 56 here. So you would see that initially, if the object was accelerating going up, if the object was accelerating going up, when the opposing force is 50, and now when the opposing force is now 56, the acceleration going up is going to decrease because the net force would have decreased. That is what you would use there. So that is what you are just supposed to do. So here they said just choose from increase, decrease, or remain the same. So you're just supposed to say it will decrease. Now we have done questions to do with what? Newton's second law and its application in terms of net resultant force. So I want us to do the last question on that, where we apply Newton's second law and the net resultant force. We are on our Newton's second law and the net resultant force. Net resultant force. How we determine any force, or else how we actually get to determine our net resultant force, given that we have got more than one force acting on our object, we have got more than one object, and then also we have got a body that is accelerating. How do we determine our net resultant force? How do we get to determine our individual forces acting on our objects? So this would be our last question, and then we then get to conclude. Thereafter, what will be left is looking into Newton's universal gravitational law. Then we are done and dusted with the Newton's laws. We will only get to know that we need to memorize Newton's first law, second law, third law, and Newton's gravitational law, and know how to apply them. So without wasting time, let's do our last question here. So now, a light inelastic string connects two blocks of masses 1.5 kg and 2 kg respectively. A force is applied in an angle 20 degree on block A. This is the force, and these are the objects or blocks. If a force of 50 newtons is applied, so if this is equal to 50 newtons on block A, the blocks move right at a constant velocity. They are saying that the blocks, they move at a constant velocity to the right, so its acceleration is definitely equal to 0. And then there is a rough surface. This is a rough surface. Therefore, we are going to have some frictional forces going that side. The tension between block A and B is 7 Newton. So the tension in between these two blocks is equal to what? To 7 Newtons. Now they're saying state Newton's second law in words. State Newton's second law in words. So I would like to take time to say that we have stated Newton's second law in words, where we say that if a net force is applied to an object, what we know is the object will start to accelerate. When it accelerates, the acceleration would be directly proportional to the net force applied, and the direction of the acceleration would be in the same direction as the net force applied. But however, the acceleration will be inversely proportional to the mass of the object. That is what Newton's second law states in words, and we have stated it earlier on. We have stated that earlier on, so I'm not going to waste much more time on stating that. We stated that. Now, they are saying calculate the kinetic friction between the 2 kg block, the kinetic friction between the 2 kg block and the rough surface. The kinetic friction If this is equal to 50 newtons, we need to resolve this force into its two components, and we know that, and we have determined that this would be F sine theta from horizontal and vertical component, and this would be F cos theta. So if we are going that side, this would be like this. So now, if acceleration is equals to 0, we know that our net force would be equal to 0. So it means that the forces that are going that side are equal to the forces that are going that side. So I would come and say that forces acting on block what? Forces acting on block A. So let me come and answer it right here. I would want to answer this question right here so that we get to see what we are saying. We want to calculate the frictional force that is acting on the 2 kg block. So I'll come and say forces acting on the 2 kg block. So I would have my net force being equal to mass times acceleration, being equal to the sum of all vector forces. And we have said that since the acceleration is equal to 0, this will be equal to 0. What are the net forces or the net vector sum of forces? We have got a force that is going to the right, so we are going to take the to the right being positive. So this one, it is going to say F cos theta minus our tension that is going to the left. We are going to say minus tension minus our frictional force that is going to go to the what? To the left as well. Frictional kinetic force is equals to 0. Now, F is said to be 50 newtons, so this is 50. Cos the angle is 20 minus the tension is said to be 7 minus Fk. That is what we are looking for, equal to 0. So I can take this and transpose that other side. So my kinetic friction now force acting on block A would be equal to 50 cos 20 minus 7. So now I now need to determine 50 cos 20. That is 46.9 minus 7. That is going to give me what? That is going to give me 39,985. So the kinetic frictional force there would be equal to what? It will be equal to 39,985 newtons. That is how you would have determined that kinetic frictional force. After that, let's now get to look into the next question. They're now saying that given that diagram, let me just get to rub through so that we can clearly see what they are saying and how we can interpret it. How will the frictional force on block A change if the angle of the force changes to 15? Now this angle is now decreasing to 15. So if this angle decreases to 15, it simply means that your F sine theta is going to decrease. When it decreases, it simply says that the force that is needed to now balance through our weight, now it is the normal force and this force. So if this decreases, our normal force is going to increase. So we are going to say that the normal force is going to increase. The normal force is going to increase. And we know that because they want to know the frictional force, we know that our frictional force is given by the coefficient of frictional force times the what? Times the normal force. So if the normal force increases, it simply means that the frictional force will increase. Therefore, the frictional force will also increase. So, in answering our question now, since we now know this, how would we have answered our question? Because here we're just trying to find logic and reasoning in accordance to what we have been given. Answering our question here, you would have just said that How will frictional force on block A change if the angle of the force changes to 15? Increase, decrease, or remain the same? You would say it will increase. Why will it increase? We say that because the normal force is increasing. So you would come and say it will increase. That was the answer that you were supposed to write for this part. You would say increase. And then here, explain your answer. You would say that frictional force, your frictional force is directly proportional to the what? To the normal force. From this equation, frictional force being equal to the what? To the coefficient of what? Frictional force times the normal force. Just like that. So you know that the frictional force is directly proportional to the normal force. Therefore, the normal force increases as the angle decreases. As the angle decreases. As the angle decreases. Thus, frictional force also decreases. Here they said what would happen? The frictional force will increase. Why is it going to increase? Because frictional force is directly proportional to the normal force according to this equation. So once the normal force increases, the frictional force will increase. Therefore, here, as the angle decreases of this applied force, we know that we are saying that this force that is going to balance our weight is going to decrease. Therefore, our normal force will increase to counteract this decrease. So the normal force increases as the angle decreases. Thus, frictional force also decreases. That is what we were supposed to do. And that is what we are simply expected to do. So now we now know how to define a force, how to define acceleration. We now know different types of forces, how to determine different types of forces, and also how to calculate them. We now know how to apply different, or else how to apply Newton's 3 laws in determining the net resultant force as well as determining different situations. So now that we know that, we now want to go ahead and do Newton's universal gravitation. So let's meet in our next video where we are going to dive deep into Newton's gravitational law. Thank you.